Questions ask about identifying whether it is exponential growth, exponential decay, or neither, and this would definitely be without a calculator. You should know what those equations look like, but this is testing to see if you know what the equations would look like. So, if it's to the x power, if the base is bigger than 1, that's when it's exponential growth. So that would be like this, and technically this, multiplying it by 2 stretches it, but it doesn't change the fact that it's still exponential growth. This one, the 8 is the base. It's exponential growth. And then sometimes, like number 2 is also exponential growth, but it's a little bit trickier to see. It's got a negative x. You need to think of it as having a positive x so that you can apply that same rule. But you can only switch it from a negative exponent to a positive exponent if you're willing to flip the fraction. So don't think of it as 1 over 5 to the negative x. Think of it as 5 to the positive x. If the base is between 0 and 1, that's when it's exponential decay. Technically, we have to say above 0 because if it's negative, that's a transformation. That's what's over the x-axis. It has nothing to do with what type of exponential it is. So here's that negative. Again, I think I mentioned a few classes ago that we're doing this exact same topic in pre-calculus. You guys different than you guys do, but that is something that they often miss. I don't give them as many friendly reminders as I give y'all because this should be new to you and it's not new to them. That is a common mistake. So if you were to switch this, then you should see the number is between 0 and 1, exponential decay. But most equations are not exponential growth or exponential decay. Everything we've done up to 2 weeks ago is not exponential growth or exponential decay. To be exponential, it has to have the variable in the exponent. X squared grows pretty quickly, but it doesn't grow exponentially. Okay, so if that seems, the reason why I put a blank here is if that's a skill that you know you've got down and you don't need to study, the idea is that you check that off and then you don't even review that at all. But if you think that you would benefit from reviewing that, then leave it blank until you do. Okay. These type of questions are also good non-calculator questions because these are asking you to evaluate a logarithm, so you have to know what it's asking you to do. This is asking you 7 to what power gives you 49, and so that's 2. So while you guys are working on doing some of this, a while back, this class period, I was creating some of those mini quizzes and I need to get those back to you. But most of the time you guys have a mistake. It's when you slip and you start to think about multiplication. You think 7 times 7 gives you 49, which is true, but that's not what this is asking. 7 to what power gives you 49? 81 to the 1/2 gives you 9. Because an exponent of half is a square root. Question 13 is the same. 5 to the 0 power gives you 1. 10 to the 0 power gives you 5 to the 0 gives you 1. 10 to the 0 gives you 1. Anything to the 0 power gives you 1. Those are very similar questions. These two, you need to apply that power rule. So I said this is the most important property of logarithms, where if you have an exponent on something that you're taking the log of, that exponent can and often needs to be brought out front. And if you think to do that, you're left with a pretty easy question. 2.8 times 1 is a to the first is what gives you a. That's how I know that's 1. Same thing with this. In the power rule, you can bring this down out front, and you get 2 times 3. 3 to the third gives you 27. 2 times 3 gives you 6. These two questions, you have to know what the ln is, and that's natural log. So if that bothers you, you can change it to log base c. That you have to know. And you can work it like the others. E to what power gives you e? It's 1. E to what power gives you 1? 0. Because anything to the 0 power gives you 1. glanced over this a minute ago. I just wrote in this base, but if there's no base written there, it's understood base 10. So this one would be 1. Okay, so for this test, we will not be responsible for these two. I still want to tell you what the pattern is because I still am suspicious that you would see that on the standardized test. The why it works takes a little bit longer, and we don't have time to do that today. So if this number is raised to an exponent of log and its base is the same number, so this number is the same as this number, of some argument, it'll simplify to just be the argument. So x to the power of log base x of 7.5 would just be 7.5. Again, I'd be happy to show you how that works out that way, but if it's not on the test, it's not really that high of importance today. So same thing. If you completely understand that and you did a good job with all those, you don't need to review what natural log means. You don't need to remember that that's understood base 10. You don't have to review the power rule. Then go ahead and check that skill off. But otherwise, leave it blank until you do. Your test will also have a couple questions about switching back and forth between logarithmic form and exponential form. Not because we particularly care about this, but this is important to us on solving some equations. So these are all exponential form. I know that because there's no logarithm. And to change it to logarithmic form, you need log out front, and you got to switch around the right two things. So x becomes the base, and 3 switch places. And that's it. No more switching around than that. 3 becomes the base, and 7 and x switch places. We're not asking ourselves if that makes sense. It doesn't have to even be true. We're just showing that we can switch it to the other form. So do log base 7 of 100 equals x, and log base 5 of 12 equals x. You should also be able to undo this. Sometimes it's good to go one direction, but sometimes you want to go the other direction. So if you want to take it out of logarithmic form, you're wanting the log to go away, but you can't just erase that. That's not, this original question is not equivalent to 2 to the 11th. It's equivalent if you switch these two things back. Take away the log if you switch these two things back. So 13 to the 100th equals t, and c to the g is 22. So that one we've been practicing a while. Hopefully you can check that one off if you need to review it later. Definitely big picture idea, but understanding the connection between exponentials and logarithmics. Why don't we just do a test on exponentials and then do a test on logarithmics together, because they're inverses of each other. Y equals 5 to the x is this inverse of y equals log base 5 to the x. 2 to the x would be the inverse, or log base 2 to the x would be the inverse of 2 to the x. So that's why these get grouped together. So, if you knew what 3 to the x looks like, which even if you don't have an idea of what it looks like, plugging in just a few points, you get it very quickly. That's what 3 to the x looks like. But, so exponential, I don't know that I need to know this at all, I guess. But if I want to graph a logarithmic function, it's often useful to say, wait, log base 2 to the x would be inverses for 2 to the x. So maybe no one says you have to graph 2 to the x. I'm going to, though. Because I want you to see that 2 to the x and 3 to the x very, very closely look to the same. But with inverse functions, all inverse functions means is you're switching input with output. So x and y becomes y and x. 1, 2 becomes 2, 1. 3, 8 becomes 8, 3. Negative 1, 1/2 becomes 1/2 negative 1. So you can copy over as many points as you need to. But that's also how you can figure out in the moment what log base 2 of x looks like. Also, notice that symmetry of y is x when we talk about inverse functions. You can also just memorize what a general parent logarithmic function looks like. They all basically look like this. Log base 2 of x looks like this. Log base 3 of x basically looks the same. I guess it would go to the right a little bit faster, and it's going to point up to this axis a little bit because they're basically the same. Same with natural log of x. If you right there in between. But this is definitely a big picture you need to know about. Yeah. So solving the equations, you can go from like one easy step to multiple steps, and this is where it starts to make some a bunch of different things. Sometimes you need to know properties, sometimes you need to know how to evaluate, sometimes you need to know how to switch between logarithmic form and exponential form. It really kind of forces you to pull all the things together, and it doesn't give you any hint about what to do. Alright, so on 32, if you had trouble starting, you need to write out that the first step is to condense those. These are both log base 10, so you can condense them into a log base 10. And because they're separated with addition, when you condense them, they're going to condense with multiplication. And that's the real trick for that person. Forcing yourself to know that condensing is likely to help you out. Now, this is one of the easier ones to solve. Log base 10 equals log base 10. That part's already equal. Now you just got to make these parts equal. So figure out where 3x equals 64, and then 64 thirds. I don't want to say this for most of these questions, but when you practice, now this will be fine for the no calculator part of the test. But when you practice, if that doesn't feel right, if you're unsure about it, there's nothing from stopping you to plug it in the left side of the equation and comparing it to the right side of the equation. Left side equals right side, and then you can be sure what you get this time. Okay, so the other way to condense was if there was a subtract sign in between them. So adding condenses to multiplying, subtracting condenses to division. These are both log base 10. When you condense them, they're log base 10. Okay, so same setup. These are already both the same type of log, so now we just need to make sure that the arguments are equal. That would be the next step. Okay, so at first glance, these look kind of the same, but it is going to be a little harder to solve at the end. You should still condense. Still condense. These are different because you don't get to just set the arguments equal to each other. This right side doesn't have an argument. It doesn't even have a logarithm. You can't just say 8x equals 3, because then you're just completely ignoring that the 8x was what you're thinking the log of. So the trick to move forward here is to say, the base is 10. This is in logarithmic form, and at some point in your head you've got to say, or at least consider, what would it look like if I put it in exponential form? And if that thought crosses your head and you do that, then you're close to finished. You just need to divide by 8, and we'd either have to give you a calculator here or make a number a little bit smaller. So if it's in a form, at least consider switching it to the other form, because oftentimes the messages come together very quickly. So that's what I was saying on the bottom of the front page. Not that we really care about switching the forms for the sake of switching the forms. We like switching back and forth between the forms because a lot of times it helps us solve these equations. It pulls them all together. Okay, so for my first grade class, these were two of the ones that a lot of people asked about for some extra practice on, so you guys are welcome to do the same thing if you want to. And to be fair, it does have one extra step of basic calculus being undone. So like, if I want to get rid of this, I would subtract 2. And if I want to get rid of times 7, I could divide by 7. Okay. So that has nothing to do with logarithms or exponentials. You should have at least done that. And then to finish this question, if you did that, it's a little more obvious. We want to finish it like we did the last question. Its current form is logarithmic form, and if we switched it to exponential form, we get something that looks a lot more manageable. To finish off. So when we first solved these equations, we did one that needed no basic algebra steps. We just switched the forms. And then you did a handful of questions where you had to undo one basic algebra step. This is the same thing, it just had 2. Undo a plus 2, and then undo a times 7. So this one, undo the plus 7, and undo the times 2. And I guess there's a lot of stuff going on in that question, so it looks a little intimidating. But again, those first couple steps have nothing to do with logarithms, nothing to do. Logarithmic form, its equivalent, exponential form, and again, the number's a little big here, so we would try to avoid that for you. But 7 to the 4th, subtract 9 from both sides, divide both sides by 7. Doesn't really reduce much. Okay, much easier question types. In fact, this is how I finished number 32 and 33. If you've got log base 12 of this stuff equals log base 12 of that stuff, then they're going to be equal as long as the stuff are the same. Just figure out where do the arguments equal each other. Add 2 base to both sides, add 6 to both sides, and divide 4 to both sides. It's nice if both sides have a logarithm and they're the same type of logarithm. So it doesn't just work for log base 10s, it doesn't just work for log base 12s, as long as it's the same thing on both sides. Natural log is going to equal natural log as long as you're taking the log of the same thing. So understanding why you can do that, I guess, is new. But to finish it out, it looks like an algebra 1 equation. Of the equations that you need to be familiar with is if you've got 5 to some power and 25 to some power. Remember we talked about you could change one of these if you want to. So instead of thinking of this as 25, think of it as 5 squared because that's equivalent. And then that's great because the new bases are the same. But if you change 25 to 5 squared, make sure that 2 goes to all of the exponent and not just the x, not just the first term. I'm going to finish this question. It's the same logic as this. This part of both sides are the same, so then we just have to make sure that these are the same. Well, now, these both have the same base, so this part's already equal. We just have to make sure that these parts are equal. We have to make sure that the exponents are set at the same way. So again, understanding what to do, you can argue it's easier than that. But if you understand how to approach the question, the actual positive steps to finish it shouldn't be too bad. If we did that on number 41, so that's saying 8 to the x, we could call this 2 to the third x. And that would be very convenient because then 2 to the 3x is supposed to equal 2 to the x plus 1, and that will be true if the exponents are the same, which happens when x is a half. Yes, I wouldn't dwell on it a lot, but you could plug that in, see that this gives you 2. And that gives you 2 square roots of 10. So you can plug it in and see that the left side equals the right side. You can check it. Sometimes, maybe not that one, but a lot of times, even without a calculator, which this would be on the no calculator part of the test, you can still check this, because if you go and plug this in, you get natural log of 6 is supposed to equal natural log of 6. So I don't know what the natural log of 6 is, but I know that the natural log of 6 equals to natural log of 6. So you can still plug it in off that. I would suspect there's a lot of stuff going in there. Condensing, switching forms, rewriting exponents, understanding why you can just set these two equal to each other. This is probably one of the biggest questions that you need to make sure that you're familiar with all of those skills so that you can do that on the test. Okay, 42 is also one you don't need to worry about for the test. However, I still want to go ahead and show it to you because I think it kind of applies here. Again, if you're not an issue bay, it would be easy to see them. So we'll just do it quick. Alright, so let's say you take the sedative and let's say 500 milligram sedative. So drugs and lots of things have half-lives, and half-life means how much time has to pass before half of it has gone away, deteriorated, been absorbed, whatever. It depends on what type of material you're talking about. And the sedative, so that would be like a pill that you took, says that it has a half-life of 30 minutes. So whatever this sedative is, wears off after 30 minutes. You should be able to determine if you would be awake after 2 hours. So you first take it when it's 0 minutes, and of course 500, that's what it starts out as. Half-life means half of it is gone in that amount of time. If this has a half-life of 30 minutes, half of it is passed. That doesn't mean that there's nothing left at 60 minutes, because it's not half of the original amount, it's half of what it was at the last half-life. So after another 30 minutes, half of that is gone. Ready to keep going? How many minutes left? 9 minutes left. So one more time. Half of that would be 31.25. So if the sedative wears off after 30, 2 hours in, you still have just enough to be put asleep. So, are you awake? I would say no. So the reason why this fits in this topic is because this is exponential decay. Half and half and half and half. If you tried to graph this, it would look like that. I guess it'd start up a little bit higher. Pretty soon, half of next to nothing gives you even closer to nothing. On a similar topic, when you take a drug for whatever reason, and this is what happens in your body, how long do you have to wait before all of it's done? When would it ever reach 0? Never, right? That's what this asymptote is saying. And that's true of when you take stuff. There is some very small trace amounts of everything that you've ever taken, because it doesn't just go away. It has half-life like that. Okay. Then we talked about this formula that is good for it's a good exponential function when something is increasing or decreasing by percent, but not compounding. Compounding would be the third or the third formula. So they want us to do a graph here, and this problem is representing an ant farm that has 20 ants. So your graph probably looks a little different than mine. I'm on the origin down here, so I know I'm only interested in positive numbers. So my x-axis is going to represent the number of days that I've had this, and I'll have the y-axis be the population of ants. So you have an ant farm, you have 20 ants, so the starting amount, I'm also going to make, and again, you're welcome to adjust yours a bit. I'm going to each one of these tick marks 10, and each one of these tick marks 1. I just think that's what would fit well. So on day 0, I have 20 ants. Well, if the population increases by 1/2 per day, it means it's increasing by 50%. Whatever it had the day before, it's got 50% more now. So if on day 0 you have 20, 50% of that would be 10, so that's how much it's increasing by. So on day 1, you now have 30. It increased by 50%. On day 2, it increases by 50% again, but not 50% of the original amount, 50% of what it was at that time. So 50% of 30 would be 15. So between day 1 and day 2, it's going to increase by 15. Between day 2 and day 3, it's going to increase by 50% again, which would be 22.5, which makes this 67.5. Of course, we won't have half an ant, but that's what we can predict. And you can plug in more and more points there. You can find out 50% of this and add it to it. So what you need to see is that that creates exponential growth. The more you have, the more it increases. So it shoots up quickly. So our function, A was the starting amount, R was the rate, so 50%. And if we're thinking of x in terms of days, it's okay, but you don't have to adjust that in those figures. Okay. The domain would be where it started and where it continues. As far as we know, it's going to continue forever. But we don't care about the ant farm before we owned it, so 0 to infinity. The range, the smallest amount of ants we had, and again, so we had to go forever, it's going to continue forever. You can quickly see that whenever hits the x-axis, the y-intercept represents where we first plotted. And in the end behavior, you've got 2 ends of this graph. This end, and you've got this end. So as x gets closer to 0, explains this, and as x gets closer to 0, y gets closer to 20. The closer you get to when you started this, the closer you get to your original amount. Now here, the further you go in time, the more ants that you're going to get. So those 15 points. Okay, we used a similar formula for 44 and compared this investment for 5, 10, and 30 years. Since that's in the exponent, we can do those. I'm going to go ahead and just squeeze them in down here, though. There's not much room up there. So the formula says if it doesn't say it's compounding, that's how you know to use this formula. So if you were talking about 5 years, I would type this, 100,000. It's like 5 in place to C. 121, 665, 29. And if you wanted to know what it's worth after 10 years, so 4% growth for another 5 years. Just like the calculator do the real work there, the formula is the important part. So, it doesn't have to be about a house, but if you somehow get a 4% return on something, $100,000 is a lot of money. But you can see the difference between leaving that money alone and letting it grow for 30 years versus leaving it alone and letting it grow for 5 years. Same thing someday when you want to retire. You can't just throw a bunch of money into a retirement fund for a couple of years and expect it to grow much. You want to throw a bunch of money or throw as much as you can afford when you're young so that it has that long time and it has more time to collect interest on the interest rates it grows. So that's the simple. Okay, we bought a car or anything and it was worth this, and 10 years later it was worth that. We should be able to compute how much of a rate increase that we got. This is its amount, ending amount. This is its starting amount. The rate, I don't know. And we've owned it for 10 years. To solve this, we're going to undo order of operations. So undo multiply first. And then to undo an exponent of 10, we would do a 10th root. Undo a square, you do a square root. Undo an exponent of 10, you undo a 10th root. And then finally, that's what 1 plus r equals. So to get rid of that, we want to eventually subtract the 1 as well. The main thing with this is you need to remember how to type that in. And the easiest way to get a 10th root is to raise it to the 1/10 power. So there's that. But I haven't subtracted the 1 yet. So there's the rate, and that would be as a decimal because that's how the formula is set up. That's how we plug it in. But if you wanted to think of it as a percent, you could move the decimal to the right two places. Okay, different investment. You buy a baseball card for $4. If it increases at a rate of 21%, how long do we have to wait before the card is worth $400? In this case, we don't know C. So like the first step here, let's go ahead and divide by 4. So we get 100. You can also add these together because it's in the parentheses. 1 plus 0.21 would be 1.21. Now to solve for time, we're just trying to solve for that exponent. So we talked about 2 ways to do this. You can take the log of both sides and use the power rule, or you could switch from its exponential form to its logarithmic form. You don't have to rearrange these, just I usually phrase it for you this way. This exponential form is equivalent to this in logarithmic form. That is the time. Time equals. So there's your exact value if you're doing something more scientific. And with our calculator, we wanted the decimal. We could type it in with the same base formula. So it's got a good return. 21% is very good. But to go from $4 to $400, that's such a great increase that it's going to take a long time. So these formulas, I used this formula for those questions because it was increasing by a percent, increasing by a percent, increasing by a percent, and decreasing by a percent. But there was not compounded interest. If it's compounded interest, that's when you can use one of these two. Either compounded continuously or compounded n times per year. And that's what you needed for the last one. It's compounded continuously. That's how you know it's per. How much is a $1,000 investment worth? You get a 2% rate after 12 years. This would either be on calculator part of the test, or what we do in pre-cals, we don't let them have a calculator, but then we just let them stop right here. Stop back and forth in this program, so we can do that as well.